Alright, hello everybody. In this video, we're going to be talking about tensors on manifolds. And, so essentially tensors are a generalization of the tangent vectors that we saw in the last video. And the idea of the tangent vectors was that they're essentially objects which can be described in terms of the local coordinates, like they have components, and these components satisfy a transition rule when on the overlap of charts in a manifold. And so tensors are essentially just a generalization of this to multiple indices. So the first thing we're going to do is look at the gradient of a function. And so the gradient, if you've seen this in like a multivariable class, right, is just, well, in that class you would probably call it a vector. It's essentially just the components are the derivatives, the partial derivatives of f with respect to each of the coordinates. Now, this turns out to be a covector. So what is a covector? Well, first let's look at what transformation rule this object satisfies, right? Because here we're defining the gradient in terms of x, right? So this is coordinate specific. So essentially, right, if we look at the partial derivative with respect to x on a chart UP, well, what is this in terms of the coordinates UQ? Well, we essentially just use the chain rule. And we end up with this. So here we are summing over beta, which runs over the dimension. So M is an M manifold. So we're summing over beta, which runs over the dimension of M. And we have, these are the components of the gradient of f on Q. And so this is essentially the transformation rule. I should write, this is Q. And with covectors, we're going to denote the index as a lower variable. Right. So essentially, in differential geometry, it's very important to get the indices in the correct spot, right? So with a vector, we denote it like this. So this is a vector. But a covector would look like this. And this is the transformation rule for a covector, right? So covector satisfies have alpha, and so this would be in the P be a sum over dx beta q over dx alpha p times the beta in the Q when we're in the Q chart, right? But for a vector, remember it was different. This is on P, say sum, where instead the derivative was flipped. Right? And essentially this, if you learn about Einstein summation, and you study this very closely, the transformation rules will become more natural in that context. So now let's look at something else, which is called the total derivative of a function. You may have also seen this in a multivariable calculus class, where we have something like this, where again alpha is being summed over the dimension. And here, right, so essentially what this is saying is that these are the components of our covector, right? Which means we can take the dx alpha, our basis elements for covector space. And these are what we call differential forms. Let me think if I'm defining this right. And differential forms are, the way to think about them is they act on tangent space, right? So technically, right, so in linear algebra there is the idea that if you have a vector space, then there is an associated dual space which consists of linear functions from the vector space to whatever field the vector space is over, right? So in this case, we're dealing with R as our field. And so in this case, differential forms are these like duals to our tangent vectors, right? Because remember, our the basis for tangent space is the partial derivatives. And so essentially, right, a differential form, for instance dx1, would act on some tangent, like 2 dx1 plus d dx2, and it just picks out this particular differential form would pick out the x1 component. And so really that's the idea behind differential forms. And differential forms are a very, very important idea in analysis. Alright, so now let's get back into tensors, right? Our goal is to generalize tensors to multiple indices, right? And so far we've only dealt with one index. So the next thing to talk about is, actually I'll do this on the next page. a Riemannian metric on M. And this is going to be is a smoothly pointwise, smoothly point-dependent positive definite form on the tangent space. So what does this mean? This means that at every point, the metric gives us essentially like a scalar product on tangent space. So we can take two tangent vectors to x and multiply them and get some real number out of that. So since we're dealing with a manifold, right, we essentially define this chart-wise. So if x is in UP, then G is given by a symmetric matrix like so. So alpha and beta are the indices denoting the positions of the matrix. And with this in mind, we can then define the inner product, right? The evaluation of the form is going to be the sum over alpha and beta of GP alpha beta like so. Right, and so alpha and beta are, again, running from 1 to m, the dimension of m. So, so in terms of this matrix, right, so when we know what chart we're on, we can essentially break down this metric into components, and we can break down the vectors into components, and we can define this scalar product in terms of those components. And so this is symmetric, so this is the same thing. And you can prove this is symmetric by just swapping alpha and beta, and since this matrix is symmetric, then it makes the product symmetric. Now, again, we can look at what happens on the intersection of two charts, right? Well, this product should not depend on what charts we're using, right? So we should have that if we compute the product using coordinates in P, and we compute the product using coordinates in Q, these should be the same result, right? But we know how to relate these vectors. We know the transformation rule for vectors, right? So we can write this GQ gamma delta. This psi term is going to give us dxq gamma over dx alpha p, and then the and so and I'm forgetting, you know, technically I should be writing the summation signs, but as I said before, the Einstein summation convention, which I may have mentioned in either episode 0 or episode 1, basically if you have a repeated index in the bottom and the top, then they are to be summed over. So that's why I'm not writing these summation signs everywhere, because it just gets redundant. Anyway, and then when we transform the eta vector, we get dx delta q over dx beta p. Like this. And so now we have that these two vectors are here. And so what this leads us to is that these two expressions must be the same. And this is the transformation rule for the metric. And so we've now given enough examples to talk about, oh crap, hold on. We've now given enough examples to talk about what is a tensor. So we say a tensor of type KL, sorry, is given by components on UP, so chart dependent components, T, so the way we're going to denote this is little P here to denote we're on the chart UP, I1 dot 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 IK, J1 dot 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 JL of X. So these are functions of X on UP. And so each of these indices is going to run over the dimension. And these functions, or components, if you like, these functions satisfy a transformation rule which is that on Q, if we have S1 dot 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 SK, T1 dot 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 TL, this is going to be equal to S1Q dx, this would be I1P so you would have these derivatives where, notice, for the upper index things, you have Q over P. But for the lower indices, we're going to have J1P or dxt1Q. For the lower indices, the derivative terms are P over Q. JLP over dxTLQ. And then times, and then again, this is going to be a large like summation over the i's and the j's. I1 dot 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 ik, J1 dot dot JL. And that's pretty much all there is to a tensor. So, we noticed we had this type thing here, right? So a metric is a type 0,2 tensor because it had two lower indices. A vector, a tangent vector, is type 1,0 because it has one upper index, and a covector is type 0,1. And so, yeah, that's all there is to a tensor, really. It's a very loaded, notation heavy, right? But in most cases, the tensors that we deal with are, typically have like at most like 3 or 4 indices. So yeah, that's it for this video, and I hope to see you in the next one.